Let's talk about another topic called polarity. Now we've been studying ionic and covalent bonds, and polarity comes across when we're talking about covalent bonds. Now we know covalent bonds are the sharing of electrons, and they can do so either equally or unequally. And when they do it equally, these are nonpolar bonds. And if they do it equally, these are polar bonds. Hence the concept polarity. Now, we also know if we have atom A and we have atom B, and they're bonding together, they're sharing electrons, we can determine whether they're equally or unequally sharing these electrons by the difference in the electronegativity, the difference in electronegativity. And we know then if they're unequally sharing on the scales that the book gives you, if it's 0.5 all the way up to 1.7 difference, this is going to be unequally sharing. If it's less than 0.5, it's going to be equally sharing, and these are nonpolar bonds. Now, there's a topic very close and similar to polarity where we talk about the overall molecule. And this is called molecular polarity. Otherwise known as dipole. Okay, so these are two different things. The bonds within a molecule can be polar or nonpolar. Then we need to look at the overall molecule to see if in fact it is polar. Now, if all the bonds are nonpolar, the molecule itself can't have a dipole, can't be overall polar. However, you could have two cases where the bonds are polar and the overall molecule it doesn't have an overall polarity. It has no dipole. And you can also have a case where you have polar bonds and overall the molecule has a dipole. And we're going to investigate how this would occur. So let's look at an example. Let's look at carbon dioxide. Now we're going to use the electronegativities in your book, and that would be figure 321 on page 115. Those are your electronegativity table for part of the periodic table and all we need. So looking at the periodic table, carbon has an electronegativity 2.5, oxygen 3.5. So each of these carbon-oxygen bonds, let's take a look, 3.5 minus 2.5, the difference is going to be 1.0 for each of these double bonds, and that's going to be a polar bond. Okay, and that means that the electrons that are being shared here, we have a double bond, so that's two pairs of electrons, they're going to be shared unequally. Now, oxygen has a higher electronegativity. Electronegativity is an atom's ability to attract electrons. Therefore, that's saying that oxygen is going to hog those electrons. They're going to spend more time around oxygen than they are around carbon. As a result, those electrons, which remember are negatively charged, are going to give oxygen a partial negative charge. Not a full negative charge. We're not talking about ions here, but it's going to be a partial charge. It's going to be negative-ish, if you will. Now, one way we can show this is through lowercase Greek delta, which looks like a little music note, and we'll put a superscript of minus. That's a partial negative charge. And on this side of the bond, carbon, since those electrons are going to be pulled away from it, it's going to be partially positive. And on this side, same situation. This oxygen is going to be partially negative, and this is going to be partially positive. So these bonds are polar covalent bonds. The question is the overall molecule going to be polar? Oh, and let me just add one other way. If you don't like Greek deltas, you can show an arrow pointing in the direction that the electron density is going, a crossed arrow pointing in the direction of the electron density. So you can either use the Greek deltas or you can use these arrows. Either one is fine. Both are acceptable. Now going back to determine whether this molecule has an overall polarity, if it has a dipole, we need to pay attention to the shape of this molecule, CO2. We have double bonds here, 2 pairs of double bonds, so this is going to be a linear molecule. And this is very important. We need to be able to determine the molecular shape in order to determine whether the molecule will have a dipole or not. In this case, we have a linear molecule. We have electrons being pulled toward this direction, toward the oxygen. We have electrons being pulled in this direction toward that oxygen. Think of it like a tug of war with carbon at the center, pulling in this direction and pulling in this direction. As a result of the pulling in this direction and the pulling in this direction, they both cancel. So this is one interesting molecule that's not going to have a dipole. No molecular dipole. No molecular dipole. Even though the bonds are polar, the overall molecule does not have an overall polarity. It doesn't have a dipole. So let's look at some molecules that do. How about water? Let's look at water. H2O. All right, Lewis dot structure. There we go. Now, let's look at this. We have 4 things around the central atom of oxygen, but 2 of them are pairs of electrons. Well, 4 things around a central atom gives us a tetrahedral shape, so the electron geometry is going to be tetrahedral, but these 2 locations here where the pairs of electrons are, really there's nothing there. So this is going to be bent, if you remember, a bent shape. Now, oxygen, periodic table, electronegativity chart, oxygen 3.5, hydrogen 2.1. We do the math. This is 1.4. This is a polar bond. Now, which one has the higher electronegativity? It is oxygen. So the electron density is getting pulled toward the oxygen. And since this is bent, think about it. We have oxygen right here. It's pulling hydrogen in this direction. We have oxygen here pulling hydrogen in this direction. The overall effect, and let me do it in a big thick brush stroke, is going to be in this direction. This has a dipole. The molecule doesn't, the overall, or the bond polarities do not cancel themselves out. In fact, they're added to here so that the molecule itself has an overall dipole. And this is very important in chemistry and in biology especially, because these dipole interactions cause molecules to become sticky to one another. Because we have the partial positive and partial negative charges on the molecules, that means, and let's just draw a little sphere here for a molecule that has a partial negative end and a partial positive end. Well, think about it. If you have another molecule of the same type, you're going to have an interaction here, electrostatic interaction between the partial positive and partial negative here. They're going to be sticky to one another. There's going to be intermolecular forces here. And that's one of the topics at the end of this chapter, intermolecular forces. Forces between molecules. And dipole-dipole interactions are very strong. The dipole-dipole action we have here in water is a special type called hydrogen bonding. It occurs primarily when hydrogen is bound to either oxygen, nitrogen, or fluorine. These are the 3 most electronegative species on the planet. And as a result, these 3 particular species cause hydrogen to be very, very partially positive. And these 3 species become very partially negative. And the more you get of a partial charge, the stronger the electrostatic interactions are. So they're very strong interactions. So strong, in fact, DNA is held together by hydrogen bonds. The base pairs on adjoining strands of the double helix are all held together by hydrogen bonds. So as you can tell, this is a very strong quasi-bond, these intermolecular forces. So we have hydrogen bonding. In this case, we would have just standard dipole-dipole interactions. where dipoles are sticky to one another. And you'll see, let's see, what else? Van der Waals forces. That's WAAL. Van der Waals forces. And this happens for all atoms, where the electrons of one atom see the proton of the other and have a transient attraction to them. Very weak, though. Very weak. Not as strong as dipole-dipole and not as strong as hydrogen bonding. So once you analyze the bonds of a molecule and determine that they are polar, in fact polar, then you have to look at the molecular geometry and see if those cancel out or are additive as they were in water. And if they're additive, the molecule has an overall dipole, and it's going to be sticky, and you're going to see intermolecular forces of dipole-dipole, or in the case of water, hydrogen bonding.